Okay. Today we uh, consider the solution of systems of equations, not just a single equation. Yeah, this is a section 2, a section 3.2, systems of equations. If I still have time, then we study section 3.3. Second topic. The secant method. Okay, now topic 1. We want to solve a system of general equations. Yeah. N unknowns and N equations. General. We can write the system in a vector form. Say, if I introduce x unknowns, I use xl to denote this vector. And the right side all are zeros. I use a 0 arrowhead to be this vector. And the function f, n functions. If I use a f arrowhead, now the unknown is x below this vector. Yeah, f1 x arrowhead, and so on. Yeah, and then the system of equations can be written as f arrowhead x arrowhead right hand side in a compact form. Okay, I want to develop Newton's method to solve the system. As an illustration, we don't consider n general. Consider a special case. N is 2. Okay, consider this case. N is 2, and take a look how we obtain Newton's method. Okay, yeah, N is 2. But consider a special case first. N is 2. Yeah, N is 2. Yeah. Now, the development of Newton's method for the system based on Taylor's field. Okay, yeah, take a look. Yeah. Okay. Consider a special case, then extend the result to general case. I want to solve these two equations. Suppose R1, R2 is an exact solution of, right? How about let me give a name to these two equations? Right? Let me call it one. Okay, yeah. R1, R2, exact solution of these two equations of one. Okay. And suppose we have obtained an approximation. Okay, suppose x1 tutor x2 tutor is an approximate solution of what? Okay. Yeah, R exact solution. X tutor approximate. Now, what I want is obtain a second approximate solution. The second approximate solution is closer to the root than the first approximate. I want to obtain a better approximate solution. That is what I want to do. Okay. Okay. Now, just like the Newton method for a single equation developed from Taylor field. Okay, very simple. Just like, okay, let me introduce error. Okay, then x1 be r1 minus x1 tutor. R, we don't know. This is we don't know. We are looking for R. X tutor, we know. So as a result, the error H, we don't know. Okay, now x2 is R2 minus x2 tutor. Then I move x tutor to left hand side. Then the root R1 is x1 tutor plus x1, and then R2 is x2 tutor plus x2. Now, next, what I want to do is estimate H. I want to estimate the unknown H. How to estimate? We use Taylor expansion. Yeah. Take a review about Taylor expansion for two variables. Taylor expansion for two variables is, yeah, expand is about x. Summation I from 0 to and 1 over I factorial h1 partial derivative, h2 partial derivative, and then I apply to x1, x2. Yeah, Taylor explained. Left side is a general function. Right side is a polynomial of x1, x2. They are not equal. So we need to add error term. Okay, error term. Yeah, it's an error. Error term. Error term, of course, depends on x1 and x2. Yeah. Okay, Taylor expansion. What I want to do is estimate the unknown h. I don't need so many terms. I just need constant term corresponding to I is 0. I is 0, constant term. And all the one term, I is 1. I just need these two terms. Now, now 2 terms. F x plus h. All right. In this sum, I pick 2 terms. I is 0. Then f x1, x2. And then plus I is 1. I is 1. Then we get h1 partial x1 plus h2 partial x2. Then apply to function n. Right. Then plus inner term. N is 1, so p1 x1. Right. Now I plug in x tilde in x. Then I get x1 tilde. This is a compare derivative first, then plug in x tilde again. Yeah. Compare derivative, then plug in x tilde. Right. Now x1, x2, they are the h1, x2 here. Then this is equals to R. Yeah, this is R. R1, R2. Yeah. Taylor expansion. Keep the first 2 terms. Okay. Keep the first 2 terms. And then plug in x tilde in x. Plug in this 2h in the h field. Okay. So that this is a 0. Because we assume R1, R2. No, not yet. This F, general F. Yeah. No, don't be confused. Yeah. So this is a Taylor expansion. Taylor. Don't be confused. All right. Apply this equation to F1 and F2. Then we get F1 x1 tilde plus h. Yeah. Apply this equation to F1 and x1 is x tilde 1. Then this h is this h. Okay. This h. Then we have this equation. How about I drop the error term? So I get approximation. After I drop the error term, approximation, then f1 x tilde x2 tilde plus h1 partial derivative f1. Then after we compute here, plug in x tilde h2 partial derivative f1 tilde x tilde. Drop the error term. Then I have approximation, not equation. Apply this Taylor expansion to F2. Then we get roughly is then plus H2 partial derivative with respect to H2. F2, sorry, F2. F2. Yeah, F2. Okay. By assumption, this is a R1, R2. This is a R1, R2. We don't know R1, R2, but we assume function F1 at R1, R2 is 0. Function F2 at R1, R2 is 0. So this is 0. 0. 0. Okay, so we have 0, 0. Yeah, let me write these two equations in matrix form. Roughly is 1. F1 x1 tilde x2 F2 x1 tilde x2. That cuts. Yeah. Okay. H, we don't know. We don't know. We don't know. We don't know. X tilde we know. Function we know. Okay. Partial x1 f compute partial derivative first. After we get partial derivative, plug in x2. Then this is a okay, here, partial. Then times the unknown h. Yeah. Times the unknown h. In this approximation, only H are unknown. Now solve this equation for H. Yeah. Move this vector to left hand side. Then move this matrix to left side. Then we get H1, H2. Roughly is negative. To save my writing, this matrix has a special name. It is called Jacobian matrix. This is a Jacobian matrix. Yeah, briefly denote this matrix by J. Okay, capital J. Yeah. Now move this vector to the left side. Then apply inverse J. Okay, then we get inverse J times F. Yeah. Yeah, the H here, we don't know. I use this way. Just mimic the derivation of Newton's method for a single equation. Yeah. Recall that we can develop Newton's method for a single equation from Newton's field. Yeah, just follow that approach. Yeah. Then we get a guess on H. Yeah, this is our application, not equal. Okay. So I use this as the estimate of the unknown H. Now cut this here. Here. So the root, we don't know. We are searching for it. Roughly, not exactly, okay, is x1 tilde, x2 tilde. Okay, now H. Now I'm cutting this for H. Then Jacobian inverse times F1, x1, x2, F2, x1, x2. X1 tilde, x2 tilde, we assume an approximation of the root. Then the right side of this approximation is a new vector. New vector. A new approximation. We believe this new approximation closer to the root than x1 tilde, x2 tilde. So we call this, okay, this is a new, consider this as a new approximation to the unknown R1, R2. Okay. Now the Newton method for two equations, two unknowns is okay, the Newton's method. The Newton's method for is, okay, This new vector, I call it x k plus 1. K plus 1. X1 tilde, X2 tilde here. The iteration in current step. Okay. Yeah. This is a next step iteration. K. X2 K. Yeah. And then Jacobian inverse. Then times here. Function F1 and yeah, K X2 K F2 X1 K X2 K. This is a Newton's method for two equations, two unknowns. Yeah, in a similar way, we can find the Newton method for general equations and unknowns and equations. But of course, in the case, we need to use Taylor expansion for n variables. Yeah, let me write down the general case. General case. Yeah. In general, in general, we have a system of n equations and unknowns. In vector form, yeah, the general is this. Now, let me introduce the Jacobian matrix for a general case. Yeah, Jacobian matrix. Of course, this depends on x. It is partial f first function with respect to first variable. This is a matrix. First row is partial derivative on the first function, f1. Yeah. So f1, x1, f1, x2, and so on. f1, xn. Suppose we have n unknowns. Jacobian matrix, first row, derivative about f1. Second row, partial derivative about f2. And the third row, derivatives about f3. The bottom row, derivative about fn. Fn. That in the general case. And a second location is for this matrix is f arrow head. This is a vector value function. Derivative on vector value function with respect to a vector means this matrix. Second location. One location, Jacobian. We call this matrix Jacobian matrix. second notation is we call this matrix derivative of a vector value function with respect to a vector. Yeah, with this notation, then Newton's method for a general case is okay. This is for n is 2 the case. Okay. And the Newton's method, method for about give a name to this equation. Equation 2 for equation 2 is xk plus 1. Yeah. The approximate solution at step k plus 1 is equal to xk. Yeah. Approximation in previous step. Then minus derivative at xk. Yeah. This notation compare derivative first. After we get the derivative, then plug in xk. Okay. Then times what? Yeah, very similar to here. Times f xk. Yeah. Where k is 0, 1, 2, and so on. This is the formula for general equation, general system of equations. Okay? Compare this formula with the Newton's method for a single equation. Newton's method for a single equation. Right? Let me erase. Yeah. The Newton's method for a single equation. Yeah. Single equation. It is xk plus 1, xk minus f xk derivative, right? You remember this formula for single equation. How about maybe the second term? I write the second term as x. I forgot take inverse here. Sorry. Because I forgot take inverse here. So this is xk minus f derivative inverse. Yeah. Okay. This is for a single equation. This is for a general system. Okay. Compare. Same in structure. Exactly same. Yeah. When this case, when n is 1, derivative actually is only this. When n is 1, this is only this, okay? Yeah, actually, exactly. So, yeah, general case, single equation case, actually, same, same formula. Right? So this is the beauty of mathematics. Let me show you one example, right, about general case. Okay, so I need this matrix, so let me erase this part. to starting with x 0, x 0. X 0 is 1, 1, 1. Okay. Carry out states iteration of Newton's method. Okay, yeah, of Newton's method to find a root of this equation: x1, x2 minus x3 squared minus 1 is 0. Yeah, three unknown. X1, x2, x3 plus x2 squared minus x1 squared minus 2 is 0. Second equation. And then E x1 plus x3 minus E x2 minus 3 is 0. To solve these three equations in three unknowns, we have to use the computer, right? By hand, impossible. And now, Newton's method. First, we need to find out Jacobian. Okay? And now, partial f1, partial x1. What is f1? Yeah, f1. This is the f1. This is the f2. F3. Yeah, yeah. Take partial derivative. Yeah. Partial f with respect to x1. So x2, x3, they are held physics. So only take derivative with respect to x1. So the answer is x2. Here. Yeah, this is x2. And now f1 with respect to x2. Yeah, f1. Take derivative with respect to x2. Only x1 left. So this is x1. Then f1 with respect to x3 left it to x3. Yeah. Yeah. Now second row derivatives for f2. F2 take derivative with respect to x1. So x2, x3 minus 2x1. Yeah. So second row. X2, x3 minus 2x1. Now f2 take derivative with respect to x2. Then x1, x2, x3 plus 2x2. Right? Okay, now negative 2x, negative 2x. Now this is f2 with respect to x3. So x1, x2. Okay, row 3 derivative about the third function. Derivative with respect to x1, so ex. Yeah. Ex1. Derivative with respect to x2, negative ex2. And then derivative with respect to x with 1. Yeah, Jacobi. Now, the Newton formula is xk plus 1 is xk minus, yeah, Jacobi. A second notation is derivative x. Yeah, yeah, second notation. Yeah, derivative k, yeah, and then inverse times function value at xk. Newton. X0 we are given. Yeah. Initial guess we are given. Now run k from 1, 2, 3, 4, 5, 6. Then stop again. Now then let me make a table. Let me erase. Okay. Newton's method, the convergence rate is order 2, very, very fast. When initial guess is close to a root, very fast. If initial guess is far from a root, then from the root that you want to find, then Newton's method may not converge faster. But when initial guess is close to the root that you want to find, very fast. Yeah. Table. Yeah. Right. Okay. X1, X4, X3. K is 0. Initial guess, of course, 1, 1, 1. K is 2. K is 1. Okay, K is 1. Yeah, yeah, here. K is 0. Then we get X1. 2.1892 and 1.594 and so on. 1.3939. Yeah, run the method. 6 steps. Okay, now when K X4 1.777674 1.42 0. Now X5 almost X5 almost have no improvement on X4. Very close. 19. Yeah. See, the first few digits match. 1.42396. 0.5. From the data, we can see that again. Just 5 steps, almost convergent. 6. Okay. According to example, we run 6 the reason. Almost no difference. Yeah, no difference. Yeah. That means Newton's method has converged with K is 6. Let me evaluate the function values at x6. Yeah, function value. Yeah, f1 at x6. What is that? Is negative 775 times 10 to negative 7. Close to 0. F2 at x6, the function value is negative 5.06729 times negative 7. Very small. Yeah. Also very small. F3 at x6. 1.7 what no 2.82299 times this. Very close to the root. At the root, function values except in 0 because x6 close to a root, so function values are very small. So just stick to the reason. Newton's method is order to have variance. I don't have time to present the second topic, secant method. Yeah, we start the topic on Wednesday.